let's talk about identifying extreme points on our curves. So specifically, we're going to be looking at identifying absolute, or also called global extrema. And what do we mean by extrema or extreme points? We mean the maximums or maxima and the minimums or minima. So these words up here are just plurals of the terms maximum and minimum that we are used to using. And as we talk about this, as we talk about absolute or global extrema, we also need to distinguish them from local. So let's start by talking about what we mean when we say a local maximum or minimum, and then we'll expand and talk about absolute or global maxima and minima. Let's start with a quick example, and I'll just sketch it off to the side here. So let's say we have our xy plane, and let's sketch some polynomial curve. And we're talking about maxima and minima, so let's identify those points there. So as I approach from the left, first of all, I know that this function is going to continue forever downward if we move to the left because it is a polynomial. And so it's going to approach negative infinity as a y value. And on the right, it's going to continue in this direction as well. It's going to approach plus infinity. So in terms of absolute maximum value of this function, it doesn't have a absolute maximum value. It's going to continue forever. Its absolute maximum is going to be positive infinity. Same with the absolute minimum. It's going to keep going down forever. There is no actual minimum value. It just extends to infinity. Let's actually modify our example here for a moment, though, just so we can focus on a different aspect of this. So I'm just going to resketch my curve here. Same basic idea. I'm just going to add an extra turning point here. All right, in this case, what is the absolute minimum value of this function? Well, it's going to be going down forever, so it's going to, approach negative infinity. So it doesn't really have an absolute minimum value. It does have an absolute maximum value, though. No matter how far I go along this curve, this value right here, let's just call it 5 to make our life easy. In this case, 5 would be our absolute maximum value. It is the highest point reached at anywhere on our curve. What about local maximum and minimum? So we know we have some turning points here, so let's identify them. We have some local maxima and a local minimum. What does it mean by local? Let's label that here. So local just means relative or within a given interval. And so when I talk about maximums and minimums, or maxima and minima, I can define either I'm trying to find the global or absolute values, the absolute highest place on the entire graph, or the absolute lowest place in the entire graph, or I may be given an interval in which I'm asked to look and identify. So maybe we're looking here. What are the local maxima and minima within this region? What are the points where there is a turning point? So like this is definitely a maximum. We see we have a concave down point with a slope of 0, or a first derivative value of 0. And similarly here, I have a concave up and a change. So I have a change in slope. So I have a minimum and a maximum, but these ones are local. So let's label these specifically. So this one here is the absolute highest point on our graph. So this is going to be an absolute maximum. And these values, right, this value right here is going to be a local maximum. And this value right here is going to be a local minimum. There is another way of defining this as well, though. So let's talk about that really quickly. Let's take a look at another curve before we get into all all our theory over here. I'm going to kind of talk about a few specific examples, and then we'll dive into it. As another example, let's say I have my xy plane. I'm given some interval to look at. So let's say I'm looking between 0 and 10, and we can be inclusive. And it's going to be something like this. All right, I have my curve, and my value of 10 is here. So I'm looking at this region right here. And let's say I'm asked to find the local maximum, or the local maxima and the local minima. So I'm like, okay, I look for turning points, local minima here and here, local maxima here and here, because I know that in order to have a maximum or a minimum, I have to have a turning point. I have to have a point where my first derivative has a value of 0. Except that's not the only part of that definition. There's a little bit more to it. I need to look at all points within this interval. And it turns out that I actually need to include the endpoints of my graph. So what do I notice here at the start of my interval when x is equal to 0? Well, I notice that that's actually higher than any other point on my graph. So my local maximum is actually going to be right here. These are also other local maximum values, but they're not the highest actual. They're not the maximum, so to speak, within my interval. And similarly for my minimums, these are local minima relative to the surrounding regions. They are minimum values. They are turning points in my graph that have a concave up curve. But this point right here, it's going to be lower than all the rest. So my actual local minimum for this interval here is going to be this point right here. So just keep those things in mind. We'll get into this in a little more detail and talk about the overall theory as we go. So let's zoom back out. Let's take a look at the writing on the slide, and let's discuss what we're looking at here. So what is the definition of absolute or global extrema? Definition A. A point x f of x is an absolute maximum on an interval if f of x is greater than or equal to f of z for every z value in that interval. So basically, if that point has the highest possible y value within a given interval, it is an absolute maximum. Definition B, a point x comma f of x is an absolute minimum on an interval if f of x is less than or equal to f of z for every z in that interval. So once again, if I'm looking at some interval and I'm finding the point with the lowest possible y value in that interval, that is my absolute minimum. An absolute extremum is either an absolute maximum or an absolute minimum. So extrema, extreme values, absolute extreme values are either going to be maximums or minimums. There's no other option. Let's talk briefly about extreme value theorem. If f of x is a continuous function for all x values in the closed interval a to b, so basically if this is my interval here, this would be point A, this would be point B, then there are points C and D in AB such that C f of C is an absolute maximum and D f of D is an absolute minimum on AB. So all that means is if this is a continuous function within my interval here, there will be some point, some value in there that is the highest possible y value or the highest possible f of x, or in our case, f of c, because they're using c to represent the point. So basically this point here would be c f of c. And there is some point that is our absolute minimum, so that would be our point here, d f of d, with the absolute lowest value within the given interval. And note, this is only true on a closed interval, like we saw in our first example here. If I don't have a defined interval and it just, continues going down forever, then I might not have an actual minimum value that I ever reach. Or if we stuck with our original curve that went up, there's no absolute max or min because it goes all the way up forever and all the way down forever. And we can also see another example here, and they've labeled it according to the notation they were just talking about. So our interval goes from A to B. There's some highest point here at C. So this point here is C f of C, and some lowest point here, D f of D. And this is a geometric interpretation of the extreme value theorem, which once again states that a continuous function f of x attains both an absolute maximum and an absolute minimum on an interval AB. Note, it may be the case that A equals C, or B equals D, or that D is less than C. All right, so that's a quick overview of what we mean when we talk about extrema, or local max and min, or global max and min. let's move on and let's dive into some practice problems. Example 1a. Find the extreme values of the function f of x equals x squared on the interval -2 to 1. And notice that we have our square brackets here, and that means that this is inclusive. This includes the points x equals -2 and x equals 1. And it might be valuable to pause and think about this for a moment on your own. How can I solve this? What do I already know about this function, about the shape of x squared? What do I know about what it means by extreme values? Do I have a closed interval? Would a sketch be helpful? Try it on your own and then go ahead and watch the solution here. So how do I do this? Well, we're going to consider all the critical points on the interval. So points where f prime of x is equal to 0, or where f prime of x does not exist. So we might have some kind of asymptote or something. Consider the values of f of x at the endpoints, and which yields the largest or smallest output. I'm going to start by looking back at the question and then just identifying some of its features. So what are we dealing with here? F of x equals x squared is a polynomial. We know that polynomials are continuous everywhere, so that's good. That's good to know. We're also given right here a set of values that we're going to look within. And so we have a closed interval. And let's start by identifying our critical points, where f of x, f prime x equals 0. And we know that a polynomial is not going to have points where the derivative does not exist. So not possible for polynomials. So that's just less work, one less thing we need to consider. So let's take a look at our original function, f of x equals x squared. Let's find the derivative, f prime x equals 2x. Let's set our derivative equal to 0. So 2x equals 0. So x equals 0 over 2, or x equals 0. This is our critical number. And let's locate that point on our graph. I know that if x is 0, my y value is also going to be 0. So 0 squared is 0. So the critical point here is 0, 0. And that's the only extreme value I have in my function at this point. I know it's a polynomial. I know it's a quadratic or parabola. I could draw a quick sketch. I don't strictly need to, and I kind of want to avoid that for now. I want us to just do it mathematically. But just a quick sketch. We know that it's only going to have one turning point, or as we've discussed in previous videos, the max number of turning points is going to be n minus 1, where n is the degree of the function. The degree of our function here is 2. So we're going to have a maximum of 1 turning point. So only one local, one extreme point, one maximum or minimum in the way that we're used to describing them. So we have considered the critical points. We also need to consider the values of the endpoints. So I know one point on my graph here, 0, 0. That's my critical point. Let's consider our endpoints. So my endpoints here are at x equals -2. So let's consider our endpoints. Let's sub those values into our function and see what we get in terms of y values. And remember, we're just subbing them into the original function because I want to know the maximum y value from my original function. I don't really care about the derivative at this moment. So f of -2 is going to be -2 squared, which is 4. So I have the point -2, 4 on my graph and within my interval. I have the point I've already considered, f of 0, which is 0. And so this isn't actually an endpoint here. So it's my critical point, but we'll still list it here just so we can compare all our values nice and neatly. And my other endpoint is when x is equal to 1. So f of 1 equals 1 squared, which is 1. So these are the 3 points I'm considering within my interval, my endpoints and my critical point, where I have a turning point occurring. So this part is done, and now we need to consider which yields the largest or smallest output. And remember, with my function machine, I put my x value in and my y value, or my f of x value, are my output. So in other words, which of these points has the highest y value? So I compare my y values here, 4, 0, and 1, and obviously 4 is my highest y value. That means that this is going to be my largest value, or my local maximum. And what has my smallest y value? That's going to be this one right here. Actually, let's use a different color for that. So this is going to be my local minimum. So let's write a little concluding statement describing what we just found here. So therefore, on the interval -2, 1, the absolute maximum of f of x, so the highest possible y value, or the highest possible f of x value, is 4 at x equals -2, and the absolute minimum is 0 at x equals 0. And let's actually sketch this situation and visualize what's happening. I just didn't want us to focus on the visuals to start. I wanted us to focus on the calculation. So let's sketch our xy plane. And every time you do this, please remember to label your x and y axis. It's really important, especially as you saw when we worked with lines and planes, that sometimes it's not an xy plane, sometimes it's a yz plane or something. So labeling your axes is very important. Let's have a quick sketch of our x squared. Also make sure you're labeling your functions in some way, especially if you're also going to put the derivative on the same graph. Very important. And we should have numbers. So yeah, I better add those in. It's a quick sketch, but if I'm going to penalize you for not having numbers, I should do it when I should demonstrate best practice for you folks as well. So -2, -4, and 2, 3, 4. All right, and so where were we looking on our graph? We were looking at, I'm going to tidy this up a little bit more. I like to keep some of these mistakes in the video so you can see that teachers make mistakes too, and also that so I can demonstrate how to fix them, so to speak. Basically, I didn't scale it properly. My x and y axes weren't matching up appropriately. That's better. All right, so we have our function and we are considering the interval of -2 to 1. So I'm going to sketch that in red. -2 to 1. So this is the region in which I was looking for local maximum and minimum values. What was my highest value here? Well, we said it was at -2, 4, and we can see that pretty clearly here, that this is the highest value in our function, the largest y value. And what was the lowest point? Well, we examined this endpoint, but we saw it was not the lowest. This point is actually the lowest. And so my local minimum value was here at 0, 0. So we can identify that visually pretty quickly, but we've also shown how to do it with calculation. I'll leave this up for a moment if you need to reflect or review anything, and then we'll move on to our next example. For our next example, 1b, we are asked to find the extreme values of the function f of x equals 1 over x plus 1 on the interval -½ and 2. We're going to go through the same checklist as before. We're going to consider critical points where the derivative is equal to 0. We're going to consider the endpoints, and we're going to compare and see which yields the largest and smallest outputs. First, we're going to consider our critical points. And in order to do that, we're going to find the derivative and set it equal to 0. So I like to rewrite my original equation first, and I'm actually going to rewrite it a little differently. X plus 1 to the power of -1, so I can use chain rule as opposed to like quotient rule. And let's go ahead and do our chain rule calculation here. And I'm going to go through that fairly quickly because we've done this a lot, but I'm just going to show my work off to the side here. I know this is a composite function because I have my outside function and then my inner function, so I'm going to use chain rule. So I've just quickly identified the pieces off to the side. If my original function is g of h, my derivative is g prime of u times u prime, and u and h are equal to the same thing. So I did my g factor, or g function first. So g is equal to u to the power of -1. G prime is negative u to the power of -2. That's just our power rule. And my inner function u is equal to h of x, which is x plus 1. And the derivative u prime is the derivative of h prime, or is the derivative h prime. And the derivative of this is just equal to 1. So I've shown my pieces off to the side here. You don't have to do it this way. I just find it convenient. And I am going through this quickly because this is something we've gone through a lot already. So my derivative is going to be, so f prime of x is equal to, it's a constant multiple rule, so the 1's just hanging out in the front there. We're going to have g prime, so negative u goes inside there to the -2, and my u is x plus 1 times u prime, which is my term here, which is just 1. And so you can see we have a couple 1's that we don't need. Cancel isn't strictly the right word here, but we're going to cancel them out. We don't need to show them. So if I rewrite my function, I'm going to have my derivative is equal to negative x plus 1 to the power of -2. Or if we rewrite it with positive exponents, it's going to be negative 1 over x plus 1 squared. So all we've done so far is find the derivative. Now we're going to need to set our derivative equal to 0. So we're going to set f prime x equal to 0. So we're going to have -1 over x plus 1 squared equals 0. And how can I set a rational function equal to 0? Well, it's only going to occur when the numerator equals 0, and I can't do that. There's no solution here because the numerator can never equal 0. And you might impulsively say, well, can't we just set the denominator equal to 0? Remember, no, we can't, because I cannot divide by 0. So instead of setting our first derivative equal to 0, maybe there are values where my first derivative does not exist. And let's consider that. So, are there places where my derivative does not exist? And yes, there are, because we know that my denominator is not allowed to equal 0. So x plus 1 squared is not allowed to equal 0. So if I take the square root of each side, x plus 1 does not equal 0. X cannot equal -1. What happens at -1? Well, I have a rational function where the denominator is going to 0. And so there's going to be a vertical asymptote at that point. So therefore, we're going to have vertical asymptote at x equals -1. But does that matter? What is our interval that we're looking at? I'm considering x values between -0.5 and 2. -1 is outside of our interval, so we don't even need to worry about it. So x equals -1 is outside of our interval. Therefore, don't worry about it. What that means is that there are no critical points within our interval. There are no points at all in this function where it will equal 0. And there's only one point where the derivative does not exist, and it is not within our interval. So we don't need to worry about it. So critical points are done. We don't have to worry about any of them. So let's talk about our endpoints. And we don't care about the derivative. We just care about the y value at these points. So we're just going to plug these values into my function, so f of negative half. And I'm not going to show my work here. You know how to evaluate functions. It's going to have a value of 2 and f of 2. Once again, I'm not going to show my work. You can do that easily enough. It's going to equal 1 over 3. So I quickly find that I have a largest value and I have a smallest value. So I've found my local maximum and minimum. So therefore, within the given interval, the local max is 2 at x equals negative half, and minimum is 1 over 3 at x equals 2. And once again, we did not need a graph in order to visualize this, but let's jump into Desmos really quick and take a peek at what the graph looks like and visually confirm that we have the right answers. So I want you to be able to answer these kind of questions without using Desmos, but Desmos is still a useful tool to quickly verify and confirm our answers. So don't rely on it, but feel free to use it once you know you've honestly figured this out on your own, and use it to just double check your answers. Switching to our Desmos view here, I've already restricted our curve to just focus on the interval we're given from negative half up to 2. And let's confirm we expect our largest value to be at negative half and 2. So our maximum value here is at negative half and 2. Looks good. And we expect our minimum value to be at 2 and 1/3. Let's confirm 2 and 1/3. So it looks pretty good. This is what our graph would look like, and we've visually confirmed our calculations. In example 2, we're going to work through the same process again. So the question asks us to find the absolute maximum and minimum values of the function f of x equals negative 2x cubed plus 9x squared plus 4 on the interval x as an element of negative 1 to 5. So we're going to consider the critical points. And once again, we can see right away this is a polynomial, a cubic function, so there's not going to be anywhere where the first derivative does not exist. We are going to consider the values at the endpoints, and we are going to see which yields the largest output or the largest y value. So let's start off by finding our critical points. And we're going to find the derivative and set it equal to 0, but I like to rewrite the original function first. So f of x equals negative 2x cubed plus 9x squared plus 4. Let's find our derivative. Nice and easy this time. We don't need chain rule or anything. Negative 6x squared plus 18x. And we are going to set our derivative equal to 0. F prime x equal to 0. And notice that this is a quadratic. We could solve it with the quadratic formula or graphing or whatever. But one of the first things you might want to do here is just take out the greatest common multiple. So I'm going to divide each term. I'm going to greatest common factor it. I'm going to take out negative 6. So I'm going to rewrite my derivative as negative 6x times x minus 3. I'm going to set that equal to 0. So negative x minus 3 equals 0. And I know when I'm dealing with factors, if any one of those factors equals 0, the whole thing equals 0. So I'm going to set each factor equal to 0. And we could probably just do this mentally, but I'll show my work. Negative 6x equals 0. X equals 0. X minus 3 equals 0. X equals 3. So these are the critical values for x that I'm going to deal with. And we'll be subbing them into our function in a moment. We're also going to consider our endpoints. So let's just list my endpoints. What am I going to be dealing with here? I'm going to be dealing with these values. So x equals negative 1 and x equals 5. Now let's test each of these points and see which gives us the greatest output and the smallest output. So I'm going to evaluate f of negative 1, f of 0, f of 3, and f of 5. And just to be super clear where we're getting these values, this one is an endpoint, this one is a critical point, this one is a critical point, and this one is an endpoint. And I'm not going to show my work, we all know how to evaluate functions, so just make sure you're working with the original derivative function, not the derivative. I'm not going to show my work evaluating, but you can do that, and you'll find that the answers are, when x is -1, y is 15. When x is 0, y is 4. When x is 3, y is 31. When x is 5, y is -21. And we can quickly see that 31 is my largest value. That's going to be my maximum. -21 is my smallest or most negative value. So that's going to be my minimum. And let's just write our concluding statement. So we've considered endpoints. We've figured out our smallest and largest. Therefore, the max value is 31 at x equals 3. And the min value is -21 at x equals 5. And if we want, we can visually confirm using Desmos. I'm not going to bother for this question. I've already demonstrated how to do that in our previous question. But if you want to double check and get a visual for what's going on, now would be a great time to do so. Our next question is the same idea, but getting a little more complicated. We are once again going to find the maximum and minimum value of our function. But what is our function? Well, let's see here. Our function is f of x equals e to the power of cosine x. On the interval, x is between pi over 2 and 11 pi over 6. As always, we're going to consider our critical numbers. We're going to consider the endpoints, and we're going to see which gives us the largest and smallest outputs. I'm not going to spend a lot of time talking about the derivative here, but we'll go through it briefly. So first of all, in order to determine our critical points, we're going to take our function, f of x equals e to the cosine x, and this is going to be a chain rule example. We can quickly remember that the derivative of e to the x is just e to the x. So we're going to have the derivative of our outside function, our e to the x, is just e to the x, multiplied with chain rule by the derivative of the inner function, which is cosine, and the derivative of cosine is negative sine x. So our derivative is going to be equal to e to the cosine x times negative sine x. And just a quick note that when we're dealing with this, x must be measured in radians. So I can rewrite my derivative, if I wish, as negative sine x times e to the cosine x. And we're going to need to set this equal to 0, and we have two factors, so let's deal with our first factor. We're going to set negative sine x equal to 0, and think about which values of sine x are 0. Maybe you want to think about that in terms of your unit circle, or we can think about what our graph of sine x looks like. I'm going to sketch that really quick here. X and y. And when is sine going to have a value of 0? Well, at 0 and at pi and at 2 pi. And we're dealing with this range of values. So does everything fit between them? Well, we're dealing with pi over 2. So starting here is our interval up to 11 pi over 6. So right around here somewhere, 11 pi over 6. So there's only one value that's admissible here, and that is, actually, sorry, we're actually dealing with negative sign here. It's not really going to change anything, but let's sketch our graph correctly. And so when does this function equal 0? It equals 0 at 0 and pi and 2 pi, but the only one that is within our interval is the value of pi. So let's just say that x is equal to pi. And our second value here, when is this going to equal 0? Well, e to the power of any value is never going to equal 0. And we could make a graph and sketch that, or we can just think some constant to the power of what equals 0. there's no number that's going to actually equal 0. We can approach 0. If it was e to the negative like 10 million, it'd be a very, very small value, but that's not really helpful at this point. Also, our values for cosine x only vary between 1 and -1, so we're never going to get anywhere close to 0. So this can never equal 0. So in terms of our critical point, we're just going to consider x is equal to pi, and then we also need to consider our endpoints. And they're given in our interval in our question up here. So we're also going to look at x equals pi over 2 and x equals 11 pi over 6. So we've considered our critical points. We've identified them. We have considered the values, and let's actually plug them in now. So let's test. So f of pi, once again, I'm not going to show my work evaluating. I'm just going to plug it in. But it's going to equal 1 over e, or approximately 0.3679. And generally, we want to keep things in the exact form. But just looking at that, you're like, well, I don't actually know what that number is. How do I compare it with the other numbers? So when we're graphing or when we're comparing, it's helpful to just write it in decimal form, because then we can quickly understand when we compare that with the other numbers, okay, yes, this is greater or less than those other values. So we've tested x equals pi. We're testing our endpoints, f of pi over 2. Once again, I'm not going to show the work, but it's going to be e to the cosine pi over 2, which is e to the 0. Anything to the power of 0 is just 1. And we're going to evaluate 11 pi over 6, which is going to give us a value of e to the root 3 over 2. Once again, exact is better, but in order to be able to actually compare the values, we'll write the decimal, which is approximately 2.3774. Now we can identify which is the smallest and which is the largest. My largest value is right here. My smallest value is right here. So let's draw our conclusion. And then we'll be good to go. Therefore, maximum is, and let's use the exact value, e to the root 3 over 2 at x equals 11 pi over 6. And minimum is 1 over e at x equals pi. Once again, now would be a great time to pause and open this up in Desmos just to confirm that we're getting the values that we expect there. We can also inspect on our little graph here. And our interval was pi over 2 and 11 pi over 6. And so what was our minimum value? Well, that was right here. So this is our point pi. Whoops, sorry, that's not our minimum value. That's our endpoint, though. Our minimum value was here at pi 1 over e. And our maximum value is here at e root 3 over 2, comma, oh, I reversed that, sorry. 11 pi over 6 is our x value. E to the root 3 over 2 is our y value. And once again, just to be very clear and specific, please use exact values in your answer. We use the rounded values here so we can actually compare, because we don't really mentally know what these values are. But it was just a tool to help us compare. We should express our final answer in exact values. I feel like this video is getting long enough, so I'm going to stop here. And in the next video, we'll continue on and look at some graphic examples and then some basic optimization problems.